All right. Hello, my name is Aaron, and I work for Collabora, and today I'm going to talk about a new way of integrating the latest machine learning capabilities into GStreamer. And it's called Python Analytics. So first of all, I'm going to talk a little bit about neural nets, some of the stuff you may already know. The neural nets have been around since the 50s. They're modeled after the way our brains work with the neurons. They were abandoned in the 80s because other techniques were superior. They didn't have GPU compute. At the time, they didn't have training data from the internet. They were revived in the 2000s by someone primarily at the University of Toronto called Jeff Hinton, and their initial success was with image recognition, object detection, segmentation, and in the last few years they've had success with language models such as speech-to-text, text-to-speech, and translation, and of course large language models like ChatGPT. So increasingly, these systems are starting to match the functionality of our own nervous system, our own brain. They can understand images, text, sensory data, and audio. And so there needs to be a way of transporting sensory data into those brains and moving the results out. In other words, they need a nervous system, and they may not realize it, but they really need GStreamer to be that nervous system. So we're going to talk about, first of all, how these neural networks work and how we can integrate it better into GStreamer. I've got an overview of some of the major toolkits that are being used. I capture in their own words what these toolkits do. The TensorFlow was originally from Google. It's been around for one of the older toolkits. It's now being surpassed by PyTorch, which was originally more for research, but now it's being used more in production. Onyx is a runtime and a file format, so you can train a model in PyTorch and then export it to Onyx format and run it in a different environment, like on Windows, for example. And there's TF-Lite, which is a lightweight version of TensorFlow, and it's popular in the embedded world because you can take your blob from the vendor and wrap it up as a TF-Lite delegate, and then clients can use a common API for those bits. I want to talk a little bit more about PyTorch. The original way PyTorch worked was called eager mode, where every ML op was executed right away, and that allowed you to reason about the model quite easily because what you specified in the model is what you actually was actually executed, and you can do dynamic flow control, but it wasn't optimized for performance because there's a lot of redundancy between the ML ops that you can't take advantage of through this approach. So the new approach in PyTorch is called compile, and in this approach, you take all the operations and you compile them into a graph. And when you do that, the ops can be fused together to reduce redundancy and save memory. In the end, these ops get turned into kernels that go into the GPU. And so you can combine 5 kernels into one. That's a much better efficiency on the GPU. And you can also target different backends. The only problem at the moment is that they have an upfront compile step which can be slow, and you have to do it each time you run the model. It would make sense to actually cache the compiled model, and that's going to be released at the end of the year in PyTorch, but you currently have that slow step. What's exciting about compile is that the performance benefits you get. So, for example, so TensorRT is NVIDIA's real-time interface, and for certain models, compile will beat TensorRT on NVIDIA hardware, which is quite astonishing. And you get all this functionality just by calling compile.compile on the Torch model. So that's exciting. And looking generally at the neural network landscape, the primary interface for these networks is Python. The primary language for machine learning is Python. And that is partly because of the repository called PyPy, which gives you access to a vast library of machine learning and non-machine learning libraries that you can just install with pip install. So it's very easy to use and very powerful, but it uses Python. And now we're going to talk about how this integrates into the GStreamer world, what we call that GStreamer analytics. An overview of GStreamer, of course, multimedia framework, but it is written primarily in C and increasingly in Rust. We do have excellent bindings for Python, and there aren't a lot of upstream Python elements at the moment, and I'm going to talk a bit about possibly why that is. There have been many attempts to integrate machine learning into GStreamer in the past. This is a list of the open source forks. GSD Inference from RidgeRun. We have GStreamer from Intel. This is optimized for Intel hardware. NNStreamer was originally from Samsung, and they focus more on the IoT type of work, sensor data. Of all those three open source forks, only NNStreamer can handle the new language models. The others are focused more on traditional object detection. And on the commercial side, we have, of course, DeepStream, which is built by NVIDIA and is focused on NVIDIA hardware and is optimized for that hardware. On the desktop, that might make sense because everyone is using NVIDIA hardware in the embedded world. There's a lot more variety of different hardware, and so this will just simply not work for other types of hardware. So we prefer to do things upstream for some obvious reasons, and so Collabora has, over the years, integrated support upstream for some of the machine learning capabilities. One of the exciting developments is the metadata framework by my colleague Daniel Morin, and this allows the rich metadata that you would generate from machine learning models to be stored and passed down through the pipeline, also to create relationships between the metadata. And he is giving a talk right after mine in the other room, so I recommend that you check that out. You'll hear about the latest of the metadata framework. We've also integrated Onyx and TF Lite inference into GStreamer, and we support a couple of models. There's the SSD model for object detection. We have FastSAM for segmentation. But as you can see, there isn't a lot of upstream support for different models. And so this year we investigated how to integrate more models into GStreamer, a different approach that's complementary to the existing one. And that's what we call Python analytics. So for this scheme, everything is upstream and everything is in Python. And because it's in Python, we get access to all the libraries, all the ecosystem. There's no impedance mismatch between the machine learning and land and the GStreamer land. It's all on the same footing, and that allows us to really easily build support for lots of new models. And it is a complement to the existing support that we've integrated in the past. So the metadata framework, it's built on top of the metadata framework, and it can work with the other native elements that are already upstream for Onyx and TF Lite. Of course, when we're talking about Python, the elephant in the room is performance. There's something called the global interpreter lock, also known as GIL. So GIL will serialize your scripts. If you try to run two scripts concurrently, GIL will make sure that they are serialized, and GIL will serialize your elements if your elements are written in Python. So you would think that that would be a showstopper for machine learning because it's so resource intensive. It turns out that we can ignore the GIL for machine learning. And the reason is that the Python elements are actually very simple. They don't do a lot of work. They're more glue between the machine learning and the GStreamer world. So they will convert GST buffers to Torch buffers and back, but they don't do much. And so all the heavy lifting is done by the framework. And so we can get away with the GIL and still get very good performance. And in our actual experience, so far it hasn't been a problem to use Python. Admittedly, we haven't created a lot of very complex pipelines, so in the future it may turn out to be an issue, and we have some mitigation plans compiling to Python. There's, I think, a proposal to give each Python element their own interpreter, so they would be running in a separate process, and so you would, then you'd of course have inter-process communication issues to deal with. But there's also, you could eventually port things to native when things are working in the Python world. We want to avoid that because that involves a lot of, it's very labor intensive because you have to find all the analogs to all the machine learning libraries. You'd have to find analogs in the C world or in the Rust world, and that's a lot of work. So we prefer to stay within Python, but that is an option. And I'm going to give you a little overview of how it all works. First of all, we have pluggable engines for the different toolkits that I talked about earlier. And I call them engines because at the moment they're doing inference, but in the future it would be cool to do training as well on a live pipeline. So they're just engines, not inference engines. We support a bunch listed over there. And then we also have a class library that manages certain infrastructure like loading the model, unloading the model, managing the device because you might want to run it on the CPU or the GPU, and managing the engine. And then we have some base classes that do generic object detection and large language models. And then we have a bunch of actual elements that run a whole bunch of models. YOLO, faster RCNN, mask RCNN are supported now. YOLO and mask RCNN can do segmentation as well. So, and then PyTorch has a hub of repository of pre-trained models that you can get access to, and all of those models are now supported up in GStreamer. You can take any of those object detection models and run them with this element. There's also Hugging Face is another repository for machine learning models, and they have a lot of the language models. And so any Hugging Face hub LLM you could load with this LLM, generic LLM element that we have in Python Analytics. So all those models are accessible now. There's a whole bunch of, and so we support the language models, we support a lot of the detection models with this approach. And of course there's more. We support OpenAI Whisper, which is a speech-to-text model. They released this under a permissive license when they were still open, and it's pretty good. There's Koki TTS for text-to-speech. Koki is a non-commercial license, and you have to purchase a commercial license, but the company behind Koki has ceased to exist, so it's a bit tricky, but it's very good synthesis. Stable diffusion is supported. There's an element that will create a picture for you if you send it text in a pipeline in GStreamer. You can ask it to create something, and it will generate the image and pass that down in the pipeline. We also support Kafka servers. If you want to send metadata out into the cloud, then you can use this new Kafka sync that will communicate with a Kafka server that's working. And all of this stuff is working. There's no special builds. There's no special branches. It's all working with 1.24 upstream. We've tested it with the distro packages, primarily on Ubuntu, and it all works right now. Where's the code? We have a merge request open. It's still in draft process because I just opened it 2 days ago. But inside you'll find all of the class libraries and the elements that I just mentioned, documentation, there's some sample data, there's a Docker file if you want to reproduce the test environment that I've been using. Future plans, we want to support multiple input streams because for batching, it's more efficient to, if you have 5 cameras and you have one model, it's more efficient to run the same model on all 5 images in a batch on the GPU rather than one by one. We also want to support CUDA Stream, which is a queue for GPUs, for NVIDIA GPUs. We already use this in the other CUDA upstream elements, so we want to share that stream, hopefully, for better performance. We plan to do some benchmarking, and we want to support more models in the future. This has been just a 2-month effort by one developer, myself. So imagine what we could do with the community in a year or more, what we could build. So we do need your help. If you want to make a new element, it's very easy to do. If you want to test existing elements on your hardware or propose different ways of using this framework, that would be great. And I want to say a big thank you to my team, colleagues at Collabora, Olivier Crete, Daniel Morin, who's giving a talk after mine, Marcus, and Vineet. Thank you very much. Open the floor for questions.
Hi, really good to see that you're adopting Python as a primary development language. And so my question is, I actually have a bunch of questions, but I'll probably go in the end. Just one important question that comes to my mind is, for use cases like STT or TTS or even LLMs and VLMs in general, the outputs would often be a bunch of tokens that keep streaming. So do you associate one GStreamer buffer per token generated by the model, or do you wait for the overall output and put the whole thing into one buffer?
That's a good question. So I guess you're thinking for STT. A speech-to-text will generate tokens, and those tokens are put together into phrases of that language. So currently we wait. We use something called voice activation detection, VAD, to detect the pauses between phrases. And so when we have a complete phrase, that's when we apply the STT. I think what you're referring to is something called streaming, where you stream the text and translate it on the fly. Currently, we don't do that, but that's something that we will be doing because you get a lot better performance at the cost of maybe more errors. But we actually use this on another project that we have called Whisper Live, which is a Collabora project that streams text, speech and text, and you can get a near live response from a language model. But currently we don't do that. We chose, we chose the path of least resistance just to get this functionality in, but we will be looking into that for sure.
Thanks. I'll catch up with you separately later on. I'll let the others go. Yeah.
Is this using just the Python GStreamer bindings, or do you have something new written on your own based on the Python C API?
No, the former. It's all using the existing bindings. And we also use the bindings for the new metadata framework, but it's all standard vanilla bindings, nothing custom.
I was just wondering what kind of performance you're getting in frames per second with the V6, for example. Well, like any of the models, like you mentioned a few, and you mentioned that you haven't done performance benchmarks, but I'm kind of wondering what's the headline here? What are we looking at in terms of frames per second?
That's a good question. I haven't worried about premature optimization, is what they say, but that will be we'll definitely. Of course, it's only meaningful if it actually gives you decent performance. I guess that's what underlying question. It just seemed fast enough to me when I was running the tests, but we will get some actual metrics to show how it actually, and of course looking into the.
So if I go to your merge request and I pull it, there's a Docker file that allows me to run this?
Yes, there, in the merge request, there's a Docker file that will you could build, and then it will run all those elements, and yeah, it's all there, right in the merge request. Yes.
Hi. My only question here is, first of all, good job on this. This is
Thanks.
something that's very important for GStreamer for the future. I was wondering whether you had given any thought to deploying this in Cerberus for Windows, because a lot of people who use PyTorch are on Windows, and getting this in their hands is probably quite important when we start using GStreamer for these purposes. So any thought on that? Any plans on that? Because the main blocker is the bindings don't work in Cerberus on Windows.
And that would be a problem. So wait, so the Python bindings don't work?
Yeah, we can't build them in Cerberus right now. It's broken.
Okay.
He was working on macOS to fix the introspection on macOS. We don't ship the bindings in Cerberus for anything right now. Python bindings.
So no Python elements in Windows.
Yeah, the problem on Windows is that when you're building against the Python interpreter on Windows, there's different versions of the interpreter. There's MSPC 64-bit, 32-bit, and then MGTOW 64-bit, and then based upon what the end user is going to be using, whatever Python interpreter is using, the libraries are different. Even the way you link them is different. So it's quite a bit of a mess to get stuff working on, like building pre-built stuff for Windows.
Right.
So ideally, we would have to actually build wheels and publish them to PyPy if you want to be able to use it. It's a significant amount of work. That's why I was wondering if you had thought about that.
In short, I haven't. But I didn't realize that was an issue. But yeah, thank you for mentioning it. Well, we're taking the path of least resistance, so not dealing with Windows at the moment. But we will have to face that at some point. But thanks. That's good too.
Hello. I was wondering, before you were saying something about the fragmentation of all the ecosystem regarding analytics and GStreamer,
right.
But then you jump into a merge request, which is going to include this as part of GStreamer. So I would like to understand a little bit, how do you foresee this fragmentation and the effects of having to merge something into the core, and what are the implications for the others?
Okay. Well, the merge request is actually not to the core, I guess you would say, but to the GST Python part of the repo. So it's not. I mean, it's Python, so it's not sitting. When you say core, I'm thinking the actual base, good, bad, the monorepo. Yeah. So this will go into GST dash Python. So, I mean, it's part of the monorepo, but it's not really, I would think, part of the core. But in terms of fragmentation, well, we hope that more people will use something that's upstream, that we all can contribute to, that we can all benefit from. And I think that's the way forward. We like to cooperate with the existing forks. The metadata is a nice way of having a common API to talk about metadata. So that's one step to reduce fragmentation that we're working on, and you can hear about that from Daniel in the next talk. But yeah, so I don't know if that answers your question, but we don't like fragmentation, but just moving it upstream is the way to eventually improve the situation where we're not duplicating efforts and we all work on the same path, I would say.
Yeah, I had a quick one. I looked into this a bit, and it kind of looked like of course, all of them require some data sets and language models, and they seem to be a lot often under a license. Like, right. What's the state right now?
Yes.
How easy is it to get someone for testing and to get one for production?
Yeah, I mean, that's out of scope of what we can do. But yeah, there's in terms of fragmentation, you have to check the license before you can use the models for different purposes, of course. And a lot of them are non-commercial because they're hoping to make some money off of these models, and so you have to check with the license for prototyping. Like the Koki TTS is a non-commercial license that we use for prototypes, but to actually put into production, you'd have to get a license or find a replacement. So that's kind of a general problem you have with, even though the model is open source, the data is not. So you have to license that data separately, and that's kind of just the nature of the beast at the moment. Yeah, but it's a good question.
Yeah, just an extension to his question, and I guess question about ecosystems in general. So I know that DeepStream, for instance, expects the input to be in the NVMe or like NVIDIA specific format. I'm sure Intel's version might expect the buffers to come in Intel specific hardware and so on. So how do you deal with that in Python Analytics, like in the plugin that you're working on upstream?
Which special formats? I mean the current maybe so to clarify which formats you're referring to.
Honestly, I can probably, if I go through the merge request, I'll understand this a bit more. But I know that the work that's happened in the fragmented offerings before this, each player has their own memory format and pixel surface format they'd like to use. Then even if you look at PyTorch versus TensorFlow, even though they're open source, PyTorch has its .pt format or Onyx, and you can either run it on the CPU or on the GPU for every PyTorch and TensorFlow model. So how do you unify that, or how do you view it when you're ingesting it into the Python Analytics element?
Yeah, we haven't, that's a good question. We haven't, like I said, at this stage, we're trying to just get that functionality merged in. And so the model now is just a GST buffer that we, not any of the, the special formats, just a regular GST buffer that we can then move to, so in system memory that we could then move to the GPU and run our analysis on. And of course, in the future, you want to keep the memory on the device as much as you can. So we will have to face that issue with conversion, and also even just row column component format. There's different expectations. I think PyTorch expects a certain format that it may not. So we have Daniel is working on CAPS negotiations using the actual metadata and the tensor formats to allow to negotiate some of those. And already the format of the buffer is, I think, part of the negotiation. Or if it isn't, we'll have to deal with that. But we're not facing that at this point in time. We're just currently it works with the system buffers and not with the exotic formats. But that's a good point. Thank you.
But it's really good initial work, so yeah.